Alright, statics fans, we are into the next module, which is about beams. Right? And once we get done with beams, we'll actually have some pretty substantive models that are relatively complete for looking at structural systems. Right? So in this first lesson of the beam modules, of which there's basically 4 or 5, depending on how you want to count the lessons, one of the first things we got to be starting to think about are real cross sections of the members, right? So when we cut a long structural member and we look at the face of what we just cut, right? There you go. There's a typical wide flange shape. The alphanumeric in the US is that a W stands for wide flange. That means both the exterior flanges, these are the flanges, those two little pieces, that's the web that connects them together. Those have parallel inside and outside surfaces to each other as compared to the standard channel, the S shape that has that inner sloping surface. Right? And this first number is the approximate height or depth, we say, of this section in inches. That'd be true of the W section as well as the S shape as well as the channel section. Right? Now the WTs are made of making a wide flange section and cutting it in half. So that's the other part that's going on here. Now the W16 by 26, that second number, is telling us the approximate weight per foot of this cross section. Right? W16 by 26. So 26 pounds per foot would be the self weight of a 16 by 26. Right? This channel is called a C shape because this shape is some version of a C, and then we have this little angle that is almost always at right angles, and the designation there, the L, is for the cross-sectional shape. 5 by 3 by 1/2. 5 is the distance of one of those legs from the back to the toe, and then the 3 would be the distance from the other one. So this would be an unequal leg angle. That's not what's drawn here. That's relatively equal leg. The half is the thickness of this, those legs of the angle. Right? These are all shapes that get put into bending, or what we would call beam kind of behavior. And in America, we have a specific sign convention that says that the bending moment that's positive would go in a way that's associated with taking the beam and bending it into a smiley face. So we're just positive people in America, right? The positive shear is as shown, and we'll go do this again and repeat this in another part of our lesson, but that's just the beginning part of things. Shearing would be take your hands together, rub them back and forth. That's the shear plane, right? So shear is parallel to the surface, whereas normal is, of course, perpendicular to the surface. In this case, the longitudinal axis of this beam is horizontal. This is a little delta x or dx of the beam length, and so the axial forces that we've been looking at before, there you would have tension. That oftentimes is called positive, and compression is oftentimes called negative. Well, shear is the force that is parallel to that surface, sort of almost like a sliding type of force. All right, let's go look at a real situation. Here's a office building from my hometown of Indianapolis, Indiana. It's a 5-story building. It's in plan view, it's an L shape, so we're seeing 2 different wings of, this would be the west wing, and this would be the south wing, right? And this is the building already completed. Here is the building under construction. We've already done steel erection. We put the metal pan deck down, and we then also have placed, not poured, but placed the concrete that forms the slab. You see also a little vertical truss here. That's for lateral resistance. Right, so we have the columns going vertical. In between the columns we have a girder, or sometimes called a floor beam, and then framing out of that we have then floor joists, and those floor joists support the floor deck, which in this case is composite of steel and concrete. Right? What you have here are partial floor framing plans, everywhere you see the straight lines, you're seeing a beam. Right? There's a lot of them. And this is done at a really tiny scale. That's the way they do these things these days. You're not supposed to actually look at the actual physical print anymore. You're supposed to go zoom in on your computer to see things. And so these columns, you can figure out the columns by location. These little circles indicate column lines, and where column lines intersect, such as here, 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 we've got 4 of those going the other way. Those are the locations of the columns, and those are, in this case, a little square because those columns are not solid steel squares. They're hollow tubes, but rectangular in cross section, so that's why their symbol was located that way, or drawn that way, as you see through here. Right? We're going to zoom in a little bit more on one of these little floor joists. Right? In between the columns is a girder that supports other beams, and then this beam or joist supports the floor slab. And so notice what we get, kind of interesting information here for this particular designer. They tell us the size of the steel beam, W18 by 40. We talked about those cross sections before. That's about 18 inches high, 40 pounds per foot of self-weight of just the beam itself. And then it's grade 50 steel. And then in this case, actually, the beam and the floor are composite together. That we have a steel beam and a concrete deck with a metal pan that forms the bottom portion of the slab. And there's a number of shear connectors. They look like bolts that are welded to the top of the beam that are then embedded inside the concrete. Or really, they're welded, and then the concrete is placed so that they are embedded together, right? And then this over here is the camber of the beam, which means that it's actually curved downwards, concave downwards a little bit, so that when we put the self-weight of the floor on there, the concrete slab, which tends to be the primary mass in the building, that will flatten out and be relatively flat. So these are cambered beams. This actually says under certain conditions what the reactions of this particular beam that the designer had turned out to estimate. Right? For us, though, we're just kind of getting an idea of what these drawings might look like in real practice. The cross-section of one of those floor joists looks like the following. So here's this W18 by 40, that I-shaped cross-section, not an I-beam. There ain't no such thing. It's an I-shaped cross-section. Here's one of these little headed shear studs that's welded through the metal pan deck, and then this represents the concrete slab that this beam is supporting, right? So joists tend to be smaller beams that support floors directly, and the typical model of one of those is going to turn out to be that we have a beam that goes such and so long and tends to be connected in a way that we would call that a simple support at either end, and for convenience we'd call that a pin and a roller. It's really a pin and a pin, but we typically just represent it as a pin and a roller. And typically under the design conditions we would have a distributed load that would be this pressure on the beam that would be something like, well, the self-weight of all the concrete and of this metal pan. That would turn out to typically be about 50 pounds per square foot. And in an office space, the live load would also be about 50 pounds per square foot. So that might be a total of D plus L, 100 pounds per square foot, and then multiplied by, if I have these spaced every so often, say every 5 feet, I would take 2.5 feet one side, 2.5 feet the other side of this load, and effectively call that then the distributed load here, which would be this floor pressure times the tributary width. So I was using 100 PSF, pounds per square foot, times, say, every 5 foot. If the beams are in center, that's pounds per square foot, times feet would be pounds per foot. That would be 500 pounds per lineal foot. I'm sorry, I was doing that off the screen, so there you go, about how that would all tend to be modeled. Right? Now, the floor beams then, or sometimes called girders, support other beams, and so their model here is we've got these other floor joists framing in. Here's the beam that we're now looking at supporting the floor, a portion of the floor slab 2, and that model would tend to look something more like this. Right? Here's this new beam that's framing in, and we've got this one of these others framing in, maybe right here, maybe right there, and the reactions that we would get over here, that would be WL over 2, WL over 2 of the joist, right? Well, that WL over 2 would become then a point load into our floor beam or girder, right? And as you look at that, you say, well, but there's two of them, right? Because you got one on either side, and sometimes, yes, we might then multiply by 2 to get all that on there. And then, because of the floor slab being partially supported, we probably end up modeling a little bit. If we wanted to be really precise, we'd end up with a portion of that slab would come in as a distributed force that would vary in its intensity. And wow, that's a pretty complicated model, and we don't like working with something like that. We'd probably smear that load out to get the equivalent effects, because we're not trying to do pure science. We're trying to do engineering, which is do it good enough. And so a simpler model here would be to do something that would look a little bit more like this. Right, I know I'm really low on the screen, so let me pull that up a little bit. Would be to lump all these triangular effects and put it into those two concentrated forces, because that would be a lot easier to work with for our beam or our girder model. Right? Now, this distinction between joist, beam, and girder, joists just tend to be real small, not have a lot of supported area. Beams may be a little bit more, but sometimes you use beam when you mean joist. Girders just tend to mean you're supporting a lot more area, and they tend to be bigger in size. And they also tend to be supporting other beams as well. Right? Let's take a close look at some basic beam behavior. Here we see a glulam beam that has split horizontally. That's pretty typical of a potential failure plane. That is a shear failure. It's horizontal shear, but it's a shear failure in that beam that's limiting things. Here you might get distracted by this elevator tower that has had problems and rotated in a global way, but sitting in front of that is this small one-story building that has these cantilever segments here that are just aesthetic. They're canopy type situations, and they have failed right in this area, the beam column connection point, in a combined bending and shear kind of failure mechanism. Right? This was an earthquake that caused that particular building problem. Right? So let's get into then more precisely talking about what goes on in our model of beam behavior. We've already talked about axial forces, and we would tend to show positive being in tension, not always, but it's a pretty common thing to do in most computer modeling. You'll see that. Right? Now, transverse shear means, transverse means perpendicular to something. Well, perpendicular to the long axis, or ultimately, shears are always parallel to something, parallel to this surface. And the symbol that we use for shear is capital V. Right? And so we have positive being indicated here, upwards on the left segment, downwards on the right. Right? Such that if you sum those two, of course, they would go away to 0, just like we have for the axial. They're in equilibrium with themselves, right? In this positive sign convention kind of manner. Right? Now, in doing this, I'm presuming you are right along with me that we're seeing the side of the beam here. That would be the long axis of the beam. So taking a little chunk out of that beam right there and bringing it down to look at. Right? Now, remember our model here that says that equilibrium can be thought about in 2 dimensions at least, in terms of 2 translations and a rotation. And we're missing that. We've got the 2 translations here. We have some sort of equilibrium in the x, some sort of equilibrium in the y, but what about rotational? And that's the bending moment. Right? So here that would be tend to be, for positive, that's going to be this clockwise, and on the other side we would have counterclockwise. Again, these would be equal opposite, and I don't remember all that stuff. So what I remember instead is I'm a pretty happy, positive person, and so positive things make me smile, and makes beams smile too. And that's what that positive bending moment looks like. That's the U.S. designer's sign convention approach to this. Right? Right? So what we're going to do in the next video segment is to go apply this to this kind of situation. Here's a beam with some loads on it, and we're going to find the internal forces at a specific point.